I want to make a deal. So you should have gotten an email from Icon/Canvas, whatever the hell, about course evaluations over the weekend. So official university course evaluations are open this week and next week. And I want to make a deal with you. There's actually two deals. Deal number one, there are 25 of you. If I can get at least 22 of you to complete a course evaluation, everybody gets a point extra credit. A full percentage point. I have no way of knowing who completed them though. I can only remind people who haven't completed it yet. So you'll all have to nag each other. But that's deal number one. If I can get a good response rate, 22 out of 25, everybody gets a full point extra credit. What do you think? Deal? Okay, that's deal number one. Deal number two, related to deal number one. It used to be that the university would let us add our own custom questions in for course evaluations, and I have a bunch of questions that I like to ask that are more specific than theirs, and they took away that option this year. So to be able to get more specific feedback about this course, I set up a Qualtrics survey. I'm going to send each of you a link via email to the survey, and if you complete that also course evaluation, so there's two different ones, I will give you another point of extra credit. And that one doesn't have to be 22 out of 25 because the way that it works is that I have a list of your emails and it tells me which emails completed a survey. So if I see that you completed one, you get your point. It does not tell me which survey you completed though. So it is still anonymous, and so I'd like your feedback as anonymously as possible. That way you can feel free to tell me good things and bad things, however you feel. So just to recap the two deals, two separate evaluations, one custom for 1 point extra credit via Qualtrics, and I'll be sending out an email link for that. And then the standard university one, if 22 out of 25 of you do it, everybody gets another point. That's my deal. The rest of the class is all available now. Since we last met, I've put up the materials for this week as well as materials for next week, and I've added 3 new articles to your reading list. So the last 2 days of class next week, and those articles are available to download in Icon under Files. So everything that is needing to be here is available. I also updated the syllabus. So there's a downloadable version that you can keep for your records that describes what actually happened in this class as opposed to what I had thought might happen. So that way you have it in case anyone wants to know what you covered in SEM, you can show that to someone. And all the materials will live on the YouTube and my website forever. So it'll still be available even after the class is over. Homework 6 is available. So that's your last thing that you have to do. I hope to have homework 5 graded this week. You'll get your feedback by next week, and that way you can decide if you want to revise it. If you do, that's due at the end of finals week along with homework 6. Homework 6 is another online opportunity to practice tests of invariance. It's worth 20 points, which means that most of you will have to do at least some of it in order to pass the class. Ha 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 ha. I learned the hard way not to make the last assignment too few points because otherwise people are like, yeah, I got a B. I'm not doing it. So you got to at least give it a shot. All right. Any questions on logistics, deals, homework 6? Not yet? All right. Then let me transition to our topic for this week. So we are transitioning into what I think people would officially call structural equation modeling. The line between confirmatory factor analysis and SEM is a little blurry. Generally speaking, if you have more than one factor at a time and you start thinking about how one factor predicts another factor, that's what people call SEM. A special case of that is what we have on tap for this week, which is higher order factor models, otherwise known as second order factor models. and versions of these types of structures that allow for method effects, bifactor models, random intercept factor models, and stuff like that. So that's what we're doing this week. Are you ready? As ready as you're going to be, right? You're here. It's Tuesday. We're going to do it. All right. The good news is that there is very little here in the way of new information. It's just putting it all together and a layer of abstraction higher than what we're used to talking about. So for right now, we're back in the world of CFA. The transition into IRT and IFA is actually not different at all because we're talking at the level of the factors, which are all continuous, normally distributed variables. So the rules for how you talk about higher order factor structures are the same, regardless of whether your items are treated as ordinal or whether they're treated as continuous. So that makes a lot of things a little simpler. So the big picture, the sequence of things that we would do in a real life analysis. So one of the things that I see naive people do when they first start trying to learn structural equation modeling, especially if they're trying to do one on their own, is to jump straight into the big model that they have in their heads. So most people have like some big ass model, 4 or 5 constructs, each indicated by multiple observed variables and some paths and stuff between them, and they fit that as the first step. I am begging you not to do that to yourself. Don't do that to yourself. Because even if you get the code right, which I'm certain you can do, trying to troubleshoot a misfitting model that has that much going on is going to be really challenging. So for pragmatic purposes, I would strongly encourage you to think of this as a stepwise kind of procedure. So for every latent factor that you are going to care about that is indicated by observed variables, one would start by specifying a measurement model per factor that is over-identified. So for each factor separately, take a look at how the items work with that factor. Make sure they all load. Test any additions to the model that you might need in terms of should it be 1 factor versus 2 factors? Do we need an error covariance for something that you can defend? Stuff like that. That way, when you combine all of the factors together, the reasons for misfit will be limited to across factor relationships. So hopefully within a factor, everything will be fine. Problems would happen between indicators that belong with different factors. So it narrows down the field of what could possibly go wrong. So for each factor, so long as it's over-identified, meaning we have at least 4 indicators, you would want to assess global model fit to the extent that you can. So does the hypothesized factor adequately predict all of the covariances between the items? That's what you're looking for. Regardless of whether you have good global fit, but especially if you don't, local fit. So local fit is the idea of going into each individual pair of the covariance between each pair of items and seeing if there's any that are predicted badly. And so this is normalized residuals in the world of CFA, which look like z-scores for how far off the model predicted covariance is from the real one in the data. It's just a residual correlation matrix in WLSMV, and it's Tech 10 output if you're using full information maximum likelihood, where it gives you chi-square tabulations of every pair of items. So the idea is to make sure that there's no pockets of your model that fit badly that you're missing by just looking at global fit. So you can have most of it be great and have one spot that's troublesome, and that still balances out to good fit, but you still want to make sure you're not missing anything. In describing the language for this in research papers, try to give them a definition of what you mean when you say like a normalized residual, or that you looked at a residual correlation matrix, because the term residual and the term error and the term residual correlation have different meanings, right? So if I have 2 indicators that have an extra relationship in the data that the model does not account for, I can add a residual correlation, right? I can add a with statement that lets the error terms of each of those variables be correlated. When I'm talking about the residual correlation matrix as a measure of local fit, that is not the same thing. So the term residual gets used in these models to refer to both the error term, so the part that's not the factor, and it's used to refer to a discrepancy. So in the context of local fit, the term residual is discrepancy. How far off is each covariance in the data relative to what the model predicts for it? That is the residual correlation matrix. One way to solve problems identified with the residual correlation matrix is to add residual correlations. The terminology is god awful. So that's why you got to help your reader. I looked at local fit as the discrepancy between the model predicted and actual correlations. Don't use the word residual. Tell them what you're looking for. That is my thanks for coming to my TED Talk, as they say. Reliability or information. Then that's the idea of effect size and precision. So that's logically separate from fit. You can have a model that fits great that has shitty reliability. That is absolutely possible. Reliability and information have to do with the strength of the factor loadings. So in a CFA context, the model assumes a linear relationship between the latent trait and the outcome, which translates into a constant amount of reliability. So you can just look at the standardized loadings and describe how strongly correlated your indicator responses are to your factor. That's effect size. So you can have really good fit, but very small standardized loadings, meaning you don't have a lot of reliability. That translates to not very much of the item is due to the factor. So that's a separate concern. In thinking about IFA and IRT models, standardized loadings are insufficient because what they refer to is the loading at the point where the item is located on the trait. It's like a conditional loading. So it doesn't mean that the item is necessarily good or bad, but where it's located, that's how good it is. And so it's something that you have to convey with a little bit more nuance. Test information, the idea of the sum of the individual item information, can tell you the range of the trait over which reliability is predicted to be adequate. And to remind you, information can be converted into reliability as information divided by information plus 1. And I would do that for your readers as well, because no one knows what the hell test information means, myself included. All right, so there's your brief review of everything that we've talked about up to this point. Questions on any of that? Okay, so once you've done this process for every factor, then you're ready to start putting stuff together. So we're talking about higher order factor models. The goal of a higher order factor model is to predict the pattern of covariance among the lower order factors. So if you have, say, 5 subscales, you think that there's one construct and it's manifested in sort of 5 different ways. That's what we're talking about here. The idea of how would you empirically test whether or not one factor underlies your 5 different dimensions. So we're talking about the structural model. And so it's very much parallel to how we talk about fit at the lower level. Before, we had indicators, and the best fitting model for them is the saturated model, right? Remember what's in a saturated model? Our friend H1. It's all indicators just get to have whatever variances and covariances they want, right? That's the answer key that we're trying to come back to. That's our best fitting model, and we're trying to see how good our HO model is relative to that one. So in the same way that the job of the factor is to reproduce the covariances among the items, at this higher level of abstraction, The job of the higher order factor is to reproduce the pattern of covariance amongst the lower order factors. So these concerns have nothing to do with the items anymore. The measurement model is set. How each factor predicts its indicators is something you would have already figured out. Now we're talking at the point where we have all the factors in the same model. The best fitting version of that is just to let all the factors be correlated. So that's what's known as a saturated structural model, where you directly estimate all possible covariances among your factors. The question of the higher order factor then is, can it reproduce those lower order factor covariances adequately? That's what we have to figure out. And so at this point, there is no distinction between CFA, IFA, or anything else, because in all of those models, our factor was thought to be a continuous variable. Theta, factor score, latent trait, whatever you want to call it, it's a continuous variable, and we are pretty much forced to assume that they're multivariate normal. There's very few exceptions to that you can specify in software without writing your own algorithm. So at the level of the lower order factors, it's like we're doing CFA because we're pretending that they're continuous. So nothing is different if you have an IFA model than if you have a CFA model, because you're just talking about how the factors correlate with each other, and factors are always continuous. Another piece of this is that we're not going to worry about means. Latent factors don't have any more information about their means than what's in the indicators. So the most common way of identifying this model is to let all either thresholds or intercepts be estimated for your indicators, and to fix your factor mean to what? This is a finger answer question. What do we typically fix our factor mean to? Yeah, 0, right? So at the higher order of the model, there's no more means. There's no additional information there. There's only variances and covariances. There are a few situations in which you would want to force the means upward. Growth models is one that comes to mind, where you want your higher order factors to change in means across time. That's not a situation that we'll talk about here, but I can help you with that if that's something you need to do someday. But in this context, we're going to keep all of the indicator intercepts and thresholds estimated, which means the factor means are 0. There's nothing to do with them up above at the higher order level. So first thing we got to do is change the way that the lower order factors are identified. So the rules for lower order factor identification, broadly construed: fix something to 1, fix something to 0. Up to this point, I had asked you to fix your factor variance to 1. That way, thinking about the change in the outcome for a 1 unit change in the factor corresponds to 1 unit standard deviation. However, you can't do that if you're planning on fitting any kind of model in which your factor is going to become a predicted quantity. You have to do it this way. So we have to switch to what's known as a marker item approach, where one of the indicators has its factor loading fixed to 1. Doesn't matter which one it is. The factor mean can still be fixed to 0, but the factor variance has to become estimated so that it can become factor variance left over after it's been predicted. Okay, I'm getting the "your internet is unstable" message. Am I frozen or am I still talking? I'm okay? All right. So this is one of the things that if you forget this, it will cause your model to blow up. Because when we have a factor that's just a predictor, it has variance. That variance can be whatever. But if a factor is an outcome, that variance has to become residual variance, right? If something is predicted, it has variance left over after the model. So we have to have variance in the factor be estimated so it can become whatever leftover needs to be for the whole solution to work. And by the way, factor residual variance has a new name. It is called a disturbance. I don't know why, but it is. So factor variance left over is disturbance. So here's one option for what a structural model would look like if we have 3 lower order factors. So each factor is indicated by 4 items. So each factor has one of its loadings for the items fixed to 1. All of the intercepts are estimated, or would be thresholds if you were in IFA land. Each item has a residual variance if you're in CFA land, and each factor has a mean fixed to 0 and an estimated variance. So with respect to the measurement model, I have 12 items times 13 divided by 2 plus 12. That's the formula that gives you degrees of freedom total, which is the possible number of item means, variances, and covariances. I got 90. Out of the 90, I've spent 33 if I estimate this model. I have 9 factor loadings because 3 of them are fixed to 1 for identification. I have 12 intercepts, and it would be however many thresholds is needed if I had categorical data instead, but it would be all of them, is my point. 12 residual variances, 1 for each item, so that's 33. So with respect to degrees of freedom, the model is very much over-identified. There's 57 more parameters I could have put in but didn't. So most of the information about model fit is coming to you because of the way that the factors predict the indicators. There's very little that's going on at the structural level. If there's only 3 factors, if I think about each of the factors as variables, as indicators of the structural model, then I've got 3 times 4 divided by 2. There's no means, and so that's why it's plus 0, that's 6. So the structural model, the number of possible factor variances and covariances, no means, just variances and covariances, is 6. This model spends all of them. So each factor gets its own variance, because these are predictors in this model. And I have all 3 possible covariances estimated as shown in the picture. So the structural model is perfect. This is as good as it gets. It is saturated. If there is a problem here, it's not at the factor level. If there's a problem here, it has to be the way that indicators relate to each other that are not on the same factor. Because ideally, you would have tested each of these separate measurement models to make sure that its set of 4 was doing good before putting this all together. Okay, are you with me? Okay, now here's an alternative way of doing the exact same thing that looks different, but it's not. Ta-da! Higher order structural model on slide 6. The measurement model, how the indicators relate to their lower order factors, has not changed. There's still 90 possible degrees of freedom, of which we've spent 33, leaving 57. What has changed is how the model addresses the variances of the factors and their covariance with each other. We still have 6 degrees of freedom because we still have 3 factor variances and 3 factor covariances as data coming in. But now, the way that I'm going to predict the covariances between the factors is as this thing up here, which I've just called HF for higher order factor. So this is supposed to be what these 3 factors have in common. A lot of you have higher order factors as part of your story. Anyone want to volunteer an example? Like child behavior checklist or other measures of childhood function. I'm thinking of Jordan. I know you have one of those, and I think Jing does too, maybe.
Yeah, I can go.
Yeah, you can go. You're going to help me out here.
Sure.
Okay.
Yeah, yeah. So the child behavior checklist roughly measures kind of child behaviors of both the internalizing, so anxiety, depression, as well as externalizing behavior problems. So things like aggression, acting out. And some of the work that I'm doing is kind of taking parent, so mother, father, and also teacher report and kind of building out a structural model looking at how they report internalizing behavior problems as one factor, externalizing as another factor, and then kind of building on top of that with a higher order factor to see kind of how do those two factors relate to one another, what unique variance could be contributed by a couple predictors, which are just a couple tasks that I've started to look at. So an emotion dysregulation task, so frustration, as well as a delay of gratification. So there's just initial look at that. Yeah, you'd have to kind of build it on top and have one internalizing factor, one externalizing, and then there's this higher order, which many call a P factor, just to see if you can, as one potential option.
A P factor?
Yeah, which would be it would make it a P factor, kind of a psychological factor, if I were to add kind of thought dysfunction as well, which
Okay.
incorporates a kind of internalizing, externalizing, and thought dysfunction. There's some literature on it, but I mean, we haven't officially labeled it that, but that's what some of the previous literature has called that behavior problem higher order factor.
Okay, so if you're a kid who has issues, then that can be manifested in internalizing and externalizing and thought, whatever you said the third one was.
Yeah,
Yeah. So
yeah, and
that's that.
there could be some relationship between them.
hmm So whether or not those three are consistent with the idea of a single higher order factor is actually not testable if you only have three. Oh, I shocked you all. Yeah. Now let's think about why that might be. Think about lower order factors. How many items did you have for a model to be testable? It was four. The same is true at this point. Yeah. So if the situation that you just described, Jordan, where you have internalizing, externalizing, and thought, whatever, as your three things, that three indicator higher order factor takes all 6 degrees of freedom. So mathematically, this model that has a higher order factor as the reason why these three lower order factors are correlated is the same as the model that just lets them be correlated. So 3 is not enough to test it unless you're willing to put more constraints, like holding the loadings equal or something like that. Kelly has a higher order factor of temperament, which is indicated by mood, approachability, adaptability, and regularity. Okay, so Kelly's in business. She's got 2 degrees of freedom left over with which to test a higher order structural model. So the idea of whether or not the pattern of factor covariances is consistent with one higher order factor is an empirical question, testable if you've got at least 4 lower order factors. Otherwise, you can't distinguish mathematically the situation where they're just related to each other from the situation where they're part of a higher order factor. You could try to make an argument based on the size of the higher order loadings, either they're consistent with a pattern where like all three of them are about the same, that would indicate a higher order factor, but you can't test it mathematically without other constraints. So I think some of you are going to be disappointed when you get to this point. But I can tell you where you might be able to be saved, Jordan, is when you said you had multiple measures. You have a teacher
Yeah,
report, parent report, and so forth.
yeah,
If you can load those up and that each dimension has 2 measures, now you're at 6.
yeah. We clustered by wave, and so there's multiple waves in the study, and so each participant gets like two or three scores, and so it kind of increased the number of indicators that we had. And then I just put in the chat here that we also, in order to get it to fit properly, had to constrain the internalizing and externalizing to be equal
hmm
onto the higher order factor.
Yep. So if you had just 2 factors then in order for the structural model with the higher order factor to be estimable at all, you would have to constrain the loadings to be equal, otherwise it's under-identified.
Yeah.
So that will fit exactly the same as just letting them be correlated. The reason why you would want to do one versus the other has to do with how you're conceptualizing the rest of the variables in the model and how they relate to it. So having a higher order factor like this is a way to rescue a trait that you had thought of as one thing in your head, but it's actually more than one thing. Because having a higher order factor here allows you to have other variables that relate to what is common across these three factors rather than each of them separately. And so that can simplify sort of a theoretical statement about how things predict each other if they can go through a higher order factor and the model fits reasonably. So once you have other information in the model, then you can start to tease apart whether it should be one thing or three things. But at this point, this model fits the same as the model that just has them covary. So this model is identified at the structural level by having all the lower order factor loadings estimated. So how the higher order factor relates to factor 1 is given by that loading, how it relates to 2, how it relates to 3. The same rules apply of identification. All factors have to have a scale. So the scale of the higher order factor is given by fixing its variance to 1. The lower order factors then don't have estimated variances anymore because now they're outcomes, not predictors, but they do have estimated disturbances, which is variance left over. And so that idea is often shown by putting a separate circle out here that's meant to convey the same type of error term for the factors as we had the e's down here for the items. So the e's down here at the item level that represent not the factor, the d's that are attached to the lower order factors, the disturbances, represent not the higher order factor. So whatever F3 has in it in terms of information that is not in common with the other two factors, that's what would be F3's disturbance variance that's left over. Okay, how we doing? Okay, watch this. Watch carefully. New model. Put your back. What'd I change? This is the same model identified differently. So rather than having the higher order factors variance fixed to 1, I identified it by fixing one of the lower order factor loadings to 1 instead. So this specification would be necessary if this higher order factor itself was to become an outcome of something else. So if you have other predictors or covariates that you think are related to the higher order factor, then its variance has to become free to become leftover variance in the same way that the lower order factor variances have to be leftover estimated variances as well. Had a question. So the disturbances themselves could be interesting too, right? Yeah. It's an empirical question once you start getting into predictive models like this. Let's say that I have internalizing, externalizing, and thought whatever. Let's stick with that. Jordan, what is thought whatever? I need a better label.
I will get the exact term for you, but I think it was just kind of thought disturbance, accounting for like mild psychoticism
Oh,
in kids, like antisocial behavior. I think it's getting a little bit at that,
okay.
but
Okay,
something that could
antisocial is
be.
something I can map onto. That's how I live my life. I've been preparing for the pandemic my whole life. So internalizing, externalizing, and antisocial. Do you think there's gender differences in those three things? In adolescent girls and adolescent boys, say, or little girls, little boys? Everyone's like, yeah, pry. Do you think gender affects internalizing to the same extent that it affects externalizing to the same extent that it affects antisocial behavior? We got some emphatic no's. I'm gonna say no, right? Isn't it that girls are more internalizing-y and boys are more externalizing-y? Something like that. I've at least seen stuff that reads like that. Well, the extent to which gender affects all of those things the same would be operationalized as a box for gender floating out here on this slide, predicting the higher order factor. Because that's what you'd be saying. You'd be saying that gender predicts whatever these things have in common, and they in turn go down to the factor level, which in turn goes down to the items. If you think, no, 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 gender affects each of these components of problem behavior differently, that's an empirical question whether the model fits better if you skip over this higher order factor and let gender directly predict each of the lower order factors. Because that's kind of what you're saying. If you have a prediction to the higher order that trickles down, that's like saying gender predicts each of the lower order to the same, that you're not losing any information. Oh, big quote in the chat window. Okay, P, higher P scores. Yeah. So if you have enough lower order factors, you can actually fit a model that has both at once. It's not always identified. I've tried it a few times and not been able to get it to go, but if you have enough, you can actually see to what extent covariates predict the lower order factors above and beyond the higher order. That is a specific type of an invariance model that's known as MIMIC, multiple indicators, multiple causes. So sometimes if people don't want to do full-on invariance testing, they can cheat their way into letting the covariates predict the indicators or the lower order factors above and beyond the higher order. So lots of possibilities there. But the point that I'm trying to make is that having this higher order factor here is sometimes a good thing and sometimes not a good thing. Because if you think of it as sort of a conduit, like if I had three factors at the lower order level that were correlated like 0.8, 0.9, I would say that's a pretty strong indicator that they're all measuring kind of one thing and they're doing so homogeneously, right? If they're all correlated 0.8, 0.9, that I'm not going to lose any information by having gender predict the one thing they have in common. Whereas if I had a higher order factor where the loadings standardized are like 0.2, 0.4, 0.3, most of their variance isn't in common. So what good does it do to have gender predict what's in common when there's not that much in common? So in thinking about what makes sense for higher order factor models, you want to think about the role of the factor. Is it supposed to be like a representative that all the effects of other things you care about go through it? Or does that not make any sense because of the nature of the lower order constructs? To some extent, these can be phrased as nested models. But the point that I wanted to make here is that if you only have three lower order factors, a higher order factor fits the same as just letting them all be related. Three is not enough. All right, how are we doing? I lost my chat window. Can I repeat the point about the factor being representative? I can try. So if I had a situation where I had three lower order factors like this, and they're all correlated strongly and uniformly, that is a pattern that is consistent with the idea of a higher order factor. There's a lot they have in common, and just having relationships of other variables to what they have in common, where the higher order factor is like a representative of all of what's below it. That only makes sense if the higher order factor plays a prominent role in the variables that are underneath it. So strong factor loadings in this type of situation are strong correlations between the factors. If your lower order factors are not that related to each other, or like if two of them are related 0.8 and the third is only related 0.2, then the higher order factor is likely not useful as a common representative because they don't have that much in common, or two of them have a lot in common and the third doesn't. What if they're related enough where you could just have them correlated but not a full higher order factor? Sure, there's nothing that stops you from sticking with this model. Where this type of model, where there are just three correlated factors, is probably a reasonable thing to do is if these three variables are only meant to be outcomes of other stuff. If I'm going to have gender and SES and all my covariates and my other predictors that I care about as predictors of these three things, that's fine. I let them be correlated. They're just three DVs. We typically assume that outcomes are correlated from the same person, and I examine how each predictor predicts each one of these things. No problem. And I would have no problem with that if these things were correlated not at all, or if they were correlated 0.8. It doesn't matter. Where this gets tricky is if these three variables are predictors in a model of other stuff that goes beyond them. So let's say that I have like a mediation model where these are my three x's, and I want them to go through some mediator, which is eventually going to go through a y. Now, what do you remember from regression about predictors that are correlated with each other? If you have predictors that are too highly correlated, it makes it really hard. Collinearity, exactly. It makes it very difficult to estimate their unique effects because they knock each other out. So if I've got three factors here that are all going to be x's in my model and they're correlated 0.8, that's not ideal. They're going to fight against each other. If they're correlated 0.8 to where they're kind of all one thing, or at least having one thing represent them is reasonable, I could turn that higher order factor into 1x, and that x represents what they have in common, and it does so while avoiding all the collinearity issues that would go into having each of these as separate predictors. So higher order factors can be useful if your factors are intended to be predictors. They may not be useful to the extent that you're interested in predicting each of the lower order factors differently, or that a higher order factor just doesn't do a good job of reflecting their common variance. So none of this has to do with model fit, right? Like that model fits the same as this model fits the same as this model. This discussion is all about how you're trying to represent the ideas of the analysis. My job is just to give you a set of options, like a menu.
I have a question.
Yeah.
So in like scale development, survey development, they always talk about domains. And I think my question got drowned out earlier in the chat, but
Sorry.
No, that's okay. Is that the same thing as like these lower order factors? Could you call them domains as well?
If you had more than one item per domain, yes.
Okay, and that makes sense. My other question then would be, if they're too highly correlated, in the past I've learned that it might mean you don't have two domains, then you only have maybe one.
Yes.
Is that correct still? Okay.
Yes, so you could test whether or not you have two domains versus one by comparing the fit of those models. It's equivalent to testing whether or not the correlation between them is less than 1.
Okay, I thought you were saying you wanted them to be super highly correlated, and so that's why I got a little confused, but I don't think that's what you said.
So our domain in your world is like a lower order factor. Is that the idea?
Yeah, that's what I was getting at. I think so.
You want them to be super highly correlated in a consistent pattern across domains if what you're hoping to find is a higher order factor that links them all together as a common thing.
Okay. I mean, because yeah, it would make sense that they're highly correlated anyway if they are of the same factor, but.
But like, so like for internalizing, externalizing, and I've already lost it again, antisocial. Like if you could have problems in one of those areas but not the other two, that's not a higher order factor.
Okay.
The idea is that like you have this thing and it causes the way you answer the questions. And some of the questions might be better questions, but they all should be affected to some extent. And
okay.
so a pattern of domain correlations that's strong, high, and consistent is consistent with the idea that there's one problem that manifests themselves in all these domains.
Okay, are you saying if you have a factor and then one of the domains that you thought was a domain within your factor isn't related to, it's not highly correlated to the other domains,
Hmm.
that it wouldn't be considered a domain of that factor? It would just be another factor?
Yes,
Okay,
I think you could phrase it that way.
okay.
Hmm.
Can I follow up on that?
Yeah.
So in just distinguishing between like when you would with with that word subdomains, when you're thinking of it as like subdomains of a single factor, it's unidimensional. It's just like a content thing where you were trying to figure out what to put into the like which items to include in the factor, for example. Um, uh, so like that's one way of thinking about subdomains, and then the next would be with just the way that we were doing it before, where you're just considering maybe you're like you have a survey and there's two separate factors, then you have like a two-factor model. The reason that you'd want to go to this level where you have a higher order factor is if you wanted to use the lower order factors, those like quote unquote subdimensions, in a different way as predictors. Is that like one of the main reasons you might want to use like higher and lower order factors that way?
If what you want to show is a relationship to what all the factors have in common, then you would want a higher order factor.
It's just like that term subdomains already like implies that they're related in some like higher way.
Hmm.
So it's like it's hard to know why you would sometimes like. So when would you, okay, because I think you answered that question before when someone asked like why wouldn't you want to, like why wouldn't you just stay with the model on page 5 with just they're just covariating with each other?
Hmm.
And you said that, go ahead.
And I said that that if
That
these are x's, that's what it was. Go ahead.
If you don't need to do any, like if you don't need to do anything with it, like if those are going to be the outcomes,
Hmm.
and that's it, they're not predictors for anything else, then you can just stay with this model.
Yeah, if these are going to be downstream outcomes only, you do not need to worry about their collinearity, so to speak. They can be related to
Okay.
each other or not, and other predictors can predict each of them in turn, and you can talk about all those relationships simultaneously, and it's cool. Where the problem comes in is if these three variables are predictors of something else, they're to the extent that they're correlated, collinear,
You
they
couldn't
will
use
fight
them.
against each other. And it
Okay.
will be very hard to say what F1 contributes above and beyond F2 and F3. And so that's where it's like, well, if they're all kind of getting at the same thing, then let's take that thing that's in common and let's make that the X instead.
Thanks.
Yeah, there's a lot of gray area here in what is reasonable versus what is possible. Like mathematically, I can tell you this fits the same as this, as this. That's what I can tell you. And that even if you can fit a higher order factor, the pattern of loadings that results from it is going to give you a sense conceptually as to whether or not that's a reasonable thing to do. So like I once had a student, so I used to do big projects in this class, and I once had a student fit this whole model where it was 5 lower order factors and she had this perfect fit of a higher order factor. But the factor loadings, these ones that mapped the higher order to the lower order were like 0.1. I'm like, okay, so you're telling me that each of these lower order factors is 99% something else. And you've got the 1% in common that you've drawn a circle around. Like, what am I going to do with that? Like, I don't care that it fits well. It doesn't make any sense. I'm getting all worked up here. All right, other questions or people who are thinking about their own data and wondering how this applies to them? Free consulting can be yours for the price of graduate level tuition. All right, so then here's another example. This is from your textbook. what could happen if you have under-identified higher order factors. So this factor structure right here is only identified if there is a covariance between the two higher order factors. Otherwise, if each of these has to stand alone, 2 is not enough. So if each of these were to have to stand alone, you would have to fix the loadings from the higher order factor to be equal to each other in order for the higher order factor variance to be identified. And at that point, it is the same thing as just letting them be correlated. The only difference is that you've taken that correlation between the factors and drawn a circle around it and given it a name. So the same rules that you learned about identification hold at the structural level. If you have two lower order factors, they can be correlated, or they can be indicators of a higher order factor if you fix their loadings to be equal, and those models will fit the same. If you have 3 lower order factors, then a higher order factor is just identified. It will fit exactly the same as just letting them be covaried. Only once you have 4 can the fit of the higher order factor be testable. But beyond just checking the fit, it would be compared to a structural model where all possible factor covariances are estimated as a new baseline, and then seeing if it's not worse after you put the structure on it. That's only a reasonable solution to adapt if the loadings are consistent with the idea that you have a higher order factor. So you can stare at a correlation matrix of your latent variables in the same way that you stared at a correlation matrix of your indicators and see where this is going to go. Tech4 is the command in M+ that you can use to generate that correlation matrix, which we'll learn about. Okay, do you want to see an example? Good answer. It was a rhetorical question, but this is a real life data example, a former student's project, and this is not her dissertation, but it was a research project that her lab had been working on for a long time. This is work by David DeLillo at the University of Nebraska-Lincoln, my first job in psychology. And he was a clinical psychology faculty who studied victimization and abuse of adolescents, young women, and children. And basically, they made up this scale of all the ways you can be mean to your children. Yeah, it's not a happy story, but the psychologists study people who have issues and also people who are doing well, but this was an issue story. So the 5 ways that they came up with based on an exploratory factor analysis, because they didn't talk to me about that part. Things that you can do to be mean to your kid: spurn them, terrorize them, isolate them, corrupt them, or ignoring. So I will tell you right here, this one's going to have a problem. Corrupting is things like leave your pot out where your kid can find it and smoke it, or leave alcohol lying around where your kid can find it and drink it. There's like a level of sort of laziness versus like deliberate being mean. And it turns out that those are not the same. So yeah, they came up with this type of item format. So there's 5 choices. And this sample of respondents is undergraduates in the Psychology 100 pool, which is a very common subject pool. So given that this sample is filled with young adults who are not expected to have more problems than usual, like it's not from a clinic or someplace, there's going to be a whole lot of skewness in these data. Most of these kids who ended up in college did not have parents who were horrible to them, right? Those things are related. So even though this is a 5-point scale, it's sort of on the like, can I call this normal? Can I CFA this, or should this be an IFA? So I did it both ways. That way we can see to what extent the results are robust to choice of a measurement model. So the background work that I did before starting this handout is summarized right here. I fit separate factor models using CFA and then using IFA to each of these different 5 factors. And by the way, if you're wondering why the number of items varies so much across the 5 scales, any guesses? Because this is what the EFA did. And also because they found out the hard way that some of the items sucked. And so they got cut from the story before the story started. So each of these factor models fits somewhere between and okay enough. So we did what we could to sort of get those into good repair before starting this process. I have the standardized factor loading summarized on the next page. And in almost every case, the loading when using WLSMV, so fitting an ordinal model to the items, is actually stronger for the same item than the loading assuming an interval linear model. So that is expected given that a linear model is probably not appropriate for items that are heavily skewed, such as in this case. Most of the people had low responses. So the first step is to reject the idea that these are really all just one way to be mean to your kid. I call this the straw man model because I don't expect it to fit. But it's going to be something that you'll have to report as a comparison for reviewer 3 who really thinks that all these things are just the same. So here is my list of variables. Note the patterns on this. I kept the spacing so that you could see that not all of the items that are in the dataset are in the model. So just as a reminder, the use variables line is used to limit just the items that you're currently going to analyze. If you forget that, it will throw everything in the dataset in the model, and it will throw it in as uncorrelated, which is going to wreak havoc on your fit. So I am starting off in CFA land. So I'm using MLR as my estimation method, robust maximum likelihood. Here are the measurement models. So there's nothing new here relative to what you've seen. I am defining all 5 factors, and the method of identification that I'm using for right now is such that all the loadings are being estimated, and so the factor variances all have to get fixed to 1. So down here, all 5 factors have their variances fixed to 1 and their means fixed to 0 for identification. And I'm showing you a cheat. That. I have fixed all of the factor covariances to 1. So that is the lazy person's way of fitting 1 factor instead of 5. That way I don't have to go back and rewrite all the rest of my code because I'm going to be working with these 5 factors for several different models. This is one way to make them temporarily all one thing just so that I can verify that the model doesn't fit and move on. So I'm going over here to my handy dandy fit statistics. There are 147 estimated parameters. My RMSEA is not terrible, and that's a function of the fact that we have 49 items in here. RMSEA likes parsimony, so only 1 factor for 49 items makes RMSEA very happy. But CFI and TLI are like, yeah, no. And the chi-square test, wildly significant. So this is our sort of straw man. Yeah, the single factor model doesn't fit. Let's see if there's actually 5 factors, and then let's see if a single higher order factor is responsible for those covariances. So this is, yeah, go ahead.
So sorry to interrupt you, but can you go back to what you just said about the straw? For some reason, my Zoom kind of kicked me out, and so I missed exactly everything that you said in that part.
Okay.
So sorry about that.
No worries. It's never an interruption, so please stop me at any point. Straw man is a phrase that just means like, this is stupid, but I'm going to do it to make a point. Like it's a model that you sort of expect to reject, but it's used kind of as a comparison because one common misinterpretation of the higher order factor is that, well, this trait is actually unidimensional. No, this straw man model is a unidimensional trait. I've set it up as 5 factors because that's the code that I'm going to need to use through the rest of the example. But by fixing all the correlations, it's correlations because the variances are 1, to be equal to 1 across all the factors, I am saying that I don't have 5 factors, I have 5 perfectly correlated factors, which reduces to 1 factor. So I'm doing this to make the point that no, this is not a unidimensional factor.
Thank you.
Sure. All right, other questions on this before I jump in? So yeah, this don't fit. Excuse me, a single factor model was examined and the fit was shown to be unsatisfactory, and therefore we continued with a 5-factor model that better aligned with our hypotheses about the fact that there was 5 different ways to ruin your child. So the code for my 5-factor model looks remarkably similar. All 5 factors loaded up at the same time, all loadings estimated. Note when I'm not typing, I'm not writing out all the intercepts and I'm not writing out all the residual variances. I quit doing that because this is like the last week of the semester and by now you all know what those look like. But I don't have to. M+ automatically estimates all the intercepts and all the residual variances, so I don't have to write them. The change to the code that actually creates the 5-factor model is by not fixing the covariances to 1, letting them be free. So listing the names of all 5 factors with the same set of names is a shortcut to estimating all possible factor covariances and letting them be whatever they want to be. Given the scaling of the model, such that the factor variances are all 1, these factor covariances are actually factor correlations. And so I reported down here the results of a rescaled likelihood ratio test comparing this 5-factor model relative to the strawman single factor model on the previous page and found this one fit way better. So we'll use this one. Here's how well it fits. RMSEA is quite happy with it. CFI and TLI are kind of like, eh. So if this were something I wanted to publish, I'd probably do some investigation to figure out which items from different factors have more in common than what the model predicts. I know because I went through the process of checking the fit within each factor that that's probably fine. The reason for this CFI being kind of meh has to do with mispredicted item covariances from different factors. But I'm going to leave that exercise to someone else. Here is the correlation matrix of my factors. So that, not the colored version, but the option to get that is Tech 4 on your output statement. There's a bunch of techs, like TECH. That's just M+ for extra output you can ask for. I think there's like 16 of them. And so you have to go through their manual to see what each of them is. And I figured out one day that Tech 4 gives you latent variable correlations arranged in a matrix, so it makes it easier to look at. And here they are. So what do you think? Are these 5 indicators of one higher order trait of being shitty to your kid? Kelly says not all of them. Yeah, this is kind of some of them, right? Like we've got this little set right here, correlated 0.8, 0.9, some more down here, but corrupting, that's the one. It looks a little different than the others. It's less related. So it'll be an empirical question whether this pattern of correlation can be adequately predicted by a single higher order factor. That's what we got to find out. And here we go. So welcome to your first higher order factor model. I want to point out a couple things that have changed. In the measurement models, I've changed the way they're identified. The first item's loading is fixed to 1. That means that the lower order factor variances are all estimated. Has to be that way because the lower order factors are going to become outcomes. Their variances are going to transform from variances into variances left over. That's not the higher order factor. The term for variance left over is disturbance. All item intercepts are still being estimated, and therefore I can keep my factor means fixed to 0. All item residual variances are also being estimated without me having to type that. Okay, so this method of identification where the measurement model has one loading fixed to 1 and the lower order factor variances estimated, this is how it has to be. If you forget, it will blow up. Okay, with me so far? Now here's the new part. I have a higher order factor, which I called abuse, because I didn't want to put shitty in a handout that went on the internet. We'll call it abuse. By each of the lower order factors, just like they were items. It's exactly the same. Each of the lower order factors has a loading that describes how the higher order factor of abuse predicts each of the lower order factors. The loadings are all estimated, which means that the higher order factor has to have its variance fixed to 1 for identification. I could have fixed one of the lower order factor loadings to 1 and had the abuse factor variance be estimated instead, but in this case, I chose to do it the usual way. So note what is no longer here that was in the previous models. What is missing? What code did I used to have that was last that is gone? The covariances. Which covariances in particular? Yeah, the covariances among the lower order factors. If you accidentally leave them in, the model will break. The covariances among the lower order factors are redundant with the higher order factor loadings. What you are saying is that those 5 higher order loadings accurately predict all possible correlations, covariances among the 5 lower order factors. That is what the model is saying. So you can't have all possible factor covariances and higher order factor loadings. It's redundant. So we can compare this model fit relative to the previous model, which is what I did right here. And the comparison is significant. 5 degrees of freedom separate this model that has a single higher order factor from the previous model that has all possible covariances among the lower order factors. Because the previous model had 10 covariances, and we're trying to approximate them with 5 loadings. That's where the difference came from. So is this good or bad? Am I happy with this result or am I sad? If I want a higher order factor, am I happy or am I sad? Wah wah, I'm sad. Yeah. Because in the same way that our HO model gets compared to H1, and we're asking how much worse is our model than perfect, I'm doing the same thing here, but at the factor level. Perfect is all possible covariances among the factors. How much worse is replacing those 10 covariances with 5 higher order loadings. This is worse. And here is where people, when they do this in practice, screw this up. They go over here and they're like, I have a higher order factor model and it fits great, see? Are they wrong? Our MSCA is very happy with this model. Does that mean the higher order factor model fits? No, because most of the degrees of freedom that are going into this global model fit have to do with the 49 items, right? The fit of the measurement model is totally swamping this. So in order to get a good assessment as to whether the structure of the factors fits, we have to have a comparison model to know what the best possible structural model is. That's what happens if you just let them be correlated. A lot of people screw this up. You will see this very frequently, people claiming all sorts of things about their higher order factors or their structural models based on the fact that the overall model fits. But most of this information that's highlighted here has to do with how the items map onto the factors. It has very little to do with how the factors map onto the higher order factor. So do I take my ball and go home? It doesn't fit. I'm done. Sorry, NIH. You paid me all this money to do research and it didn't fit, so I got to figure out why, right? So in the same way that if we had bad fit for items to the factor, we looked at how the items were mispredicted in terms of their covariance, we can look at how the higher order factor loadings mispredict the lower order factor covariances. And that's what we'll do next time. All right, questions before we adjourn? Okay, then you all may take your balls and go home, or stay home, as it were. Let me know if you need anything. Otherwise, I hope to see you Thursday for the exciting conclusion of 5 ways to be shitty to your child. Peace out.